Hello, Stephen.
Can you hear me all right?
Very well.
Good.
Yes. Yeah, I wanted to say that very quickly because people will join. I've been reading through your papers, Stephen. They're very helpful.
Good.
The one there's actually So there's one the question. I'll wait till people are there about the insulation. I didn't understand why I entitled it, but I'll ask that later. Though the calculations from, I think you're saying Julius Lingo, perhaps one or two others, calculating the albedo from the number of is it called the cloud droplet number or something like that, and the optical depth. So I've been learning a lot about clouds in the last few weeks. A lot of it's thanks to you reading those papers.
Well, I'm struggling to learn about them, but
yeah. Well, I'm reading around as well.
Yeah. The Julius Lingo thing was maybe a year or two ago, so it's probably a bit hard now. That's where the 1.7 came from.
So what's 1.7?
Saying that
radiated forcing
is 1.7 per meter.
Radiated forcing. Hi. I was only saw one person. Hi, Sev. Yes. Good to see you too. Yeah. 1.7 radiated forcing. Okay, because I took from it the number of there's a huge, to power of 24 or something, number of droplets that's needed. I think in the air at any one time.
It'll be 10 to the 20 something.
Yeah.
I'm getting 10 to the 17 a second at full power from the spray vessels.
Right. Yeah. Okay. Yeah, and I watched last week's meeting, which I couldn't be there because I was trying to get something finished, and watched that again this morning. And it's criminal, really, that your solution is so well. The marine cloud brightening solution is so powerful,
and so ignored.
Yeah.
The key really is the energy you need to make a new condensation nucleus is its surface area times the surface tension of water.
Yeah, you mentioned that. I saw that.
And then the energy that's reflected by the enormously big drop that grows on it.
And a final talk on ecosystem from PV. They're going to be short, so we're going to have a quick turnover.
What's going on here?
I'm looking forward to hearing from all of you. So we'll start off with David. David, do you want to introduce yourself? And I'll let you go from there.
Yes, I can do that. Thank you.
What's that noise?
Just checking if you can see my slides there and if you can hear me well.
Yeah, you sound great and you can see the slides.
Have we got a cross channel, some cross interference or something here?
Here at the University of Campinas.
Can anyone hear another noise?
Yeah, I can.
Sorry for not being there.
I don't see anything.
Seems to have something on.
I guess you can imagine this is far away from being.
Has someone got the radio on? I can only see 5 people. Let's just
see. You might need to mute.
But who do I mute? Because I'm looking at 5 people. You haven't got the radio on, have you, John?
No.
And
let's mute in turn.
Okay. Right, okay, let's all mute.
I chose to do super quick presentation, 3 points, super quick, that I think are important when
cross-link to the conference that's going on in Colorado.
Right.
I suppose.
Oh, no. I wonder if I should
we log out and log in again?
Yeah.
Oh, no, just mute Stephen.
Clive,
you can do it. Stephen can't mute himself.
It was Stephen. Stephen, I've muted you, and the sound went away. Can you hear me, Stephen? We can't. Sorry, we can't hear you now because I've muted you. You have to click to unmute. I think I have to sort of. I've asked you to unmute you, so you should be able to unmute now. And if you try and say something, we'll know if you. Right. That noise is back again.
that the forest.
You don't have a radio on or some noise going on?
The carbon sink.
Because
strain
we can
of
hear.
forest
Is it another conference?
is getting reduced.
Perhaps, Stephen, if you don't mind, just
Strain of the
disconnect and
utility is
reconnect.
really-
No, he just has to mute.
Well, but we'd like to hear him speak, though.
Yeah.
Uh,
If he's-
if he
Log
has
on,
to
log
stay
on.
muted, it means he can't speak today.
Behavior or even.
May I suggest, Stephen, it's not. I think it's not your fault, but somehow or other there's some
By the
crosstalk
next decade,
interference.
If Stephen would log off and log on again,
Yeah,
that might help.
That's right, Stephen.
right.
Do you mind just log off and end, sort of leave, and then come back again?
About to do that.
Yeah. Sorry about that. Well, don't know how that happened.
Hi, Brew.
Hello, Sev. Hi, everybody. Hi, Clive.
Hi, Brew,
Robert, France.
and
Brian. Good to see you all.
absolutely,
We got off
absolutely.
to quite a vocal start, but it wasn't real. It was an overlap.
What's that, John?
I was just telling Brew we got off to quite a vocal start.
Yes, that's right. Yes, some sort of overlap with someone else's conference.
Yeah.
Well, it's time to begin. And hi, Brian. Always good to see you, Brian. And Franz. And okay, and I watched the last week's, and thanks for hosting it, Robert. I'm in awe, basically. So anyway, there we go. We these conversations, and Chris said he won't be coming today. So let's get on with it. There isn't time to think, really, is there? To think about sort of significance of things. You just have to get on with it. Okay, agenda. So yeah, what do we want to talk about today?
So I was actually hoping that Chris would be available again today to continue the debate that I think it was mainly Brian and him and others, Rob perhaps was having over the question about the level of production in the ocean deserts, or the low productive areas of the ocean, as he calls them.
Yeah.
And whether the question is whether abundance is good. I mean, I think he said that it should be fine to bring it back to the status quo, the level of the production it was originally, but boosting it beyond that is an interesting debate, and what would be the consequences of that?
Yeah.
That seems counterintuitive, doesn't it? Generally,
Doesn't it?
the more life, the better. The more rich it is, the more biodiverse, the more it absorbs CO2, the more it deacidifies, all those things.
Yeah.
Well, it's
Does
a
it really
question.
matter where it is? Does it really matter if the ocean deserts become highly productive? Is there a downside to that?
It's a question of baselines.
Yes.
Keep calling on baselines, which are way too recent. I was, reading up some stuff that Dave King was talking about, and bringing whale numbers back to 1900 levels, where actually, of course, we've got that map of the whaling grounds, which is 1888 date or something like that, which shows vast areas of abandoned whaling grounds. So there's huge damage done, over the preceding century.
Yeah.
So what
we
was the
can talk
condition
about.
of the?
Sorry,
we
John.
can talk. Yeah, that's right. But
Yeah, should
I think
we can have a discussion
Yeah.
without Chris. Maybe we can raise some questions to put to him next time.
Okay.
So ocean abundance. Welcome back, Stephen.
Hi.
And there's no noise, so I think we did the right thing there.
So I had been listening to the conference in Colorado during the day, and they were on switch. They should have switched off, but I hadn't. So I'm sorry, it's my fault.
Oh, okay. All right, never mind. It's all sorted.
And the whole day they mentioned marine cloud brightening for about 2 minutes in a very busy way.
Stephen, you were just saying the increase or decrease in radiative forcing caused by bubbles. You didn't finish your comment.
Well, I was talking about the ratio of the energy that you need to make the initial condensation nucleus, which is its surface area times its surface tension. You compare that with the energy that's reflected, the solar energy that's reflected by the drop that grows on that nucleus. Okay, and the manufacture of the initial drop is only 8% efficient, and the reflectivity is also quite low. But even when you put those in, you're talking about a ratio of 1 billion to 1. So you've got this enormous leverage because of the reflectivity of the big cloud drops. And that's what makes it go. The energy that we're using to make the spray is tiny. 300 kilowatts for a few hundred vessels. It's an amazing energy gain. I don't know anything as big as that.
Yeah, we could say some more about that. I was saying before people came, there's this picture here in one of Stephen's papers. I was just saying to Stephen before we began that I've been learning a bit more about clouds and droplets and things and calculations. This picture here which is in one of your sort of short papers, Stephen, shows the insolation at the top of the atmosphere at different times of the year in different parts of the world. So this is 90% north and and the Antarctic, and interesting that there's more. So I'd quite like to, I don't know, for you to explain a bit more about that.
Well, there's more going into the.
Not now, Stephen. Not now. If that's okay, I'll just put it on the agenda.
Okay.
I'd love to do it straight away, but let's put it on the agenda. So, So insolation diagram. Explain. All right. It's just saying explain. Yep. That's my own request. Perhaps I'll put. Anyway, that's right. That's for Stephen to talk about. That'll do. Anything else for anyone else?
Do we know who of us is going to COP27 and whether they can say it, whether they can push any of our ideas on SRM?
We can talk about that.
I thought Brian might be going, but I don't know.
Brian?
Brian is muted.
Yeah.
I'm not going. I'm actually just helping to host the climate benefit concert that starts this weekend with Sumitra Das at the Healthy Climate Initiative.
Right. HCI.
I went to Copenhagen and Glasgow, and I thought they were a complete waste of time. And it's quite expensive to go to Egypt for a couple of weeks, so I'm not going.
I've got some hopes about this one, actually, whereas it didn't have much in the ones beforehand.
Okay, let me put down hopes then. And then let's discuss. Then you can. That'd be good. I mean, we all need a lift. Anything? Anyone else?
Perhaps if we could also discuss the atmospheric river over Australia at the moment.
Oh yeah.
Okay.
Yeah.
Australia.
We also talk about extraordinary heat in Europe and the UK at the moment.
Yeah. It's ridiculous.
Yeah.
It's far too mild. Yeah. Okay.
It can swing in both directions, of course, so maybe we'll get a terrible January and February. Everything seems to be changing more slowly. And if you have a model of instability and tipping points, you can get a prediction for them, how close you are to them if things go more slowly. If your model is a ball rolling in a shallow dish and another shallow dish next door, which it could flip over into, the rolling period of the ball gets longer if the curvature of the dishes changes. So it's a predictor of something being near a tipping point.
Mm. Yeah, I think I see what you mean. I can imagine something like that, Stephen. Well, or any publications or anything else? Maybe there's enough to talk about here.
The conference in Colorado is being recorded, and you can download it and listen to everything.
Right.
It's very much concentrating on stratospheric aerosol. But
Okay.
I'll dig out the links to it. You can record it. It goes on for 2.5 days. We've come to the halfway through the first day.
Right. Okay. But it might be good to. You've been listening to it then.
Downloadable, or is it something you got to download after the whole conference is over?
Sorry, Brian, about the conference when it's over.
Wondering if it's immediately downloadable day by day, or something that you just wait until the whole conference is over.
Okay. Can it be downloaded day by day, Stephen?
Yes, and the links are to it. You can listen. You can tune into it, and they publish the agenda, so you can choose which bits of it you want to go to, and you can slide up and down the time scale. So that's being organised very, very well indeed.
Yeah. Yeah. I'm surprised not to see John listen. Perhaps he's listening to that conference, because that'd be up his street.
Might very well be, yeah.
Yeah. Yeah.
I didn't notice him. There was a picture of the whole gathering. I didn't see him there, but I may have been not paying enough attention.
Okay. Anything else, or should we start talking? So what about the ordering here? We just start from the top?
Yeah. Okay,
then. Yeah, I mean, I find it hard to yes, as Brew just said, what about baselines? I suppose my understanding of what Chris Vivian says is yes, if you there's certain ecosystems, certain sort of biodiversity, and if you go and swamp it with something else, then you might lose some things. Maybe that's what he's saying.
But where there is almost no life and no biodiversity, where it's virtually a clean slate like the deep dark blue ocean, I can see no reason why growing kelp there, growing phytoplankton there, increasing krill and fish stocks there couldn't be just about entirely beneficial.
Yeah.
Yes, but because the starting point, a lot of the purists say, well, you've got to introduce species which are endemic to the area. But if there's nothing there, then there's nothing to be endemic. But
there's something there. It just doesn't have the nutrients to flourish. So
I remember being told by someone who knew about it that everything gets everywhere. If it's got, so it may not be there now, but it will get everywhere as soon as you supply the temperature or the nutrients or the oxygen or whatever you want.
Yes.
Everything gets everywhere.
Makes sense.
But certainly, rather than predicting what the marine biodiversity could be if it's boosted, surely the sensible thing is to turn the clock back and observe, as Bruce says, what it was like. And if there is evidence of the greater productivity in some of these, like the mid-Pacific areas, it'd be very interesting to produce that and say, well, let's at least return it to that and go further. But there would be a lot of information about what was like 100 years ago in those areas as well, wouldn't it? Do you know much about that, Brew?
Well, yeah, I was just thinking, let me dig out that map and just pull it up for you all so that we can see it. I've just posted it somewhere.
The Hawaiians have probably got very good oral history, and the Tahitians on how fish stocks were and what was caught there, 300 and 400 years ago. They're very, any society which doesn't have literature normally has a very strong oral
Yeah.
history tradition.
Yeah. Well, if you let me share screen, let me just pull
Hold on a minute. Yeah. Okay.
is that share screen, share that screen, share. Right now, can you see that map?
Yep. Yep.
And let's full screen it, make it large as I can, and blow it up. Right, so in the legend down the bottom here, the dark areas, this map was produced in 1884. The dark areas are the whaling grounds as exist then, and the lightly shaded areas are the abandoned whaling grounds.
Yeah.
Can you see my mouse hand over this?
Yeah.
Yes.
Look at this. This is huge tracts of the Pacific, which are pretty much ocean deserts now. And these justifiable whaling grounds with sailing ships.
There's 4 times as much area which has been abandoned versus what was there in 1884.
Exactly. Now, for the whales to have been there, there had to be a mass of phytoplankton and krill and other stuff.
Yeah.
It's colossal.
That's fascinating. Yeah.
It really is. I mean, and very probably, given the dates of this, you've got a sort of generation, you've got to think 50 years of a working generation at that time. They'd already been doing damage here. Probably even greater areas were full of whales. So, certainly, because you look up around the United Kingdom, up here, where and this part of the North Atlantic, where they've been fishing whales really hard since sort of 1500. Those were abandoned before the knowledge of these abandoned whaling grounds.
Yeah.
So the whole ocean was alive, and this is the point that I make about life. Constantly colonizes and stabilizes. That's the nature of nature. That's what it does. And if you disrupt the nutrient cycles, then it collapses and falls away. But if you nurse it back into life, it will come, as Stephen was saying. It will build up. What we're trying to do is build it back up quickly.
Well, I know the Nantucket whalers had a huge industry. And if you look at North America, the area around Nantucket is empty of whales. And we knew from that huge industry that it would have been really full of whales.
Well, at 1500, when they first got to the Newfoundland cod banks, they were scooping cod out of the water with baskets. Yeah. And there were tales of ships sailing into shoals of fish that were so large that it slowed them up.
Yeah, I actually grew up on Cape Cod and I went diving 100 times a year and never saw a codfish to this day.
Yeah.
The oil from whales was supplying all the oil for light.
Yeah.
So if you think about the production of the fossil fuel industry today, that was actually being done. The equivalent of it was being done by the whales.
Yeah.
Yeah, well, literally, the whale blubber lit the lights that allowed the guys to sit in the drawing rooms and design the steam engines.
Yeah. Yeah,
it's fascinating. But it's, to me, this is understanding.
And you'll also notice that the Southern Ocean, the southern parts of it, haven't got any entries on it virtually, and that's because with ice flows and that, it was hard for sailing vessels to navigate there.
Yeah, you couldn't get down.
As soon as steamships came round, the whalers could go down there and really make a huge mess of it.
Yeah. South Georgia.
Yeah. So my question is, what's the sort of meaning of what sort of significance of this? I mean, I think we're saying that.
Well, this takes me back to my biomass argument, and that biomass study of the total amount of biomass. That document says we've reduced the total amount of life on the planet by at least 50%. And you can look at those maps of how much of the planet was forested and how much we've taken out and how much damage agriculture has done over the past 4,000 years. Think of the whole North Africa and such like. So with all that additional life on the planet, life was self-regulating because you had so much more going up there for cloud formation, so much more movement, and it's evidence that it's capable of doing it. And bear in mind, 550 gigatons of new life on the planet, or restored life on the planet, that's enough to take your CO2 levels right back down to around 300 parts per million. Making allowance for what we put into the atmosphere now, and an allowance for significant off-gassing from the oceans. So people think of the planetary mechanisms for temperature regulation, and actually the sweating of the planet, the transpiration of trees and what comes off it. This is a primary mechanism. Probably before the greenhouse gases. Greenhouse gases obviously have control of it as well, but there's a lot more to it than meets the eye, I suspect.
Gaia is the main regulating thing for Earth, and we've basically knocked off 4/5 of Gaia already. So we've only got 1/5 operating in the oceans at any rate. Probably only half on land.
Yeah, I mean, it would be really interesting if we could find sedimentary studies. Brian, you may know about this, evidence of life that's been lost over the past 500 and 1,000 years. And I suspect that it's there if you go and look for it in the sediments of different parts of the ocean.
Friends, yeah.
I wanted to say, if there is more heat, when the whales have been there must have been there also much phytoplankton.
Exactly.
And also this life which is daily going up and down, up to 1,000 meters, like the lanternfish and so on.
Yeah,
and also the whales went up and down, and so you have a better intermixture between the fertilizing lower layers to the less fertilized upper layers.
And not only that, Franz, but you had huge shoals of large fish that were moving up and down through the layers feeding. So there was a massive amount of circulation in the ocean going on, which we've lost.
And if the phytoplankton was 3 times as dense in the surface waters, the albedo would have been considerably lighter then.
The turquoise planet, not the blue planet.
Yes. And additional, you're speaking of the sediments. You don't need to look for phytoplankton in the sediments because it had been eaten by the food chain. So you must look for other kind of, if a fish falls down, it will not oxidize on its way down.
Yeah, good point.
While the small phytoplankton particles become oxidized. That surely had been not a case in these old times.
Yeah, and a whale fall is an amazing bounty for a benthic community, and you get hagfish and sharks and predators of all kinds on the seafloor, and those were decimated by almost 1,000 to 1 over that period. And it's interesting, those light gray zones actually corresponded to zones of mesoscale upwelling, lots of little eddies, baroclinic lows and things of that sort that would naturally bring nutrients up to the surface just through cyclonic action, akin to the convectant system of a cyclone or a hurricane or something.
That diagram is very persuasive, Brew. And I mean, I think a lot of people really have trouble visualizing what we're talking about, and we're but this is really historic restoration. I mean, who wouldn't be on board? Who wouldn't?
Go back and read the reports of the early explorers. So Captain Cook's log is all online, and you can find sections in that where there's a description of somebody coming around a headland, and there's shoals of manatee and such like, who's passing by the ship for hour after hour after hour.
And the Polynesians, of course, traversed the ocean, and Kon-Tikis and all those things. They caught plenty of catch on the way because they survived.
Yeah.
So they must have been there.
You don't see it now. It was much easier to catch, and of course they didn't have the tools to catch things with we do now.
Yeah.
Therefore, there had to be so much more life in the ocean.
Their hooks were made out of shells, laboriously over a few days to make one fish hook.
Yes.
Bring that back as a new regulation.
No, the smaller numbers, but as I said, so much of this happens on land as well.
So we're looking really to counter when the IMO, and I watched it all 2 weeks ago with Chris. No, you can't do that. That's dumping, or you can't. You're not allowed to put iron because that's dumping. We're trying to find a way to say, look, for goodness sake, or people say that's nutrient robbing. You put iron and then it'll use up all the phosphate and something, and then there'll be nothing left. I think we're looking to say that, if you allow the life to thrive, as long as you don't immediately hoover everything up, and sell it somewhere in a fish shop, then it will continue the mixing. It'll bring back that mixing from lower layers. The whole thing.
You nurse it back into life. It's the iron that comes from Sahara dust and such like, which lands on the Atlantic, sinks down through the water column. It isn't around long enough for the tropic cycles to establish themselves. But once they're there and it's working, then they capture it, and it stays there because it's churning through the whole cycle of life, and it stays in position.
Yeah.
You need to
the more life you have there, the more that Sahara dust is captured.
Yeah, exactly. Exactly.
And recycled.
And I understand, of course, is the elegance of your system with the buoyant flakes, which is why I like it so much, because you're allowing nursing it back into life, putting the minimum amount of iron into the ocean, but keeping it available.
And that iron is all from waste sources.
Exactly.
I can send a paper about a way to increase the iron. There were lots of experiments done on this, but they tipped an enormous amount in of quite big lumps, and only one of the experiments actually produced any useful measurements of carbon change. And I think what they were really measuring was how good people were at keeping track of which bit of sea they treated. And this is quite difficult. They were only there for a very short time, and you could easily get muddled up about the bit that you had just squirted the iron into. What I would want to do is to have the iron injection taken place over much lower quantities over a much longer time. So there's time for things to migrate and
for an ecology to develop rather than just the lowest level. And
the way I want to do it is to reverse things called cathodic protection, which is used for stopping corrosion in oil platforms. And if you do this the other way around, you can increase the rate of corrosion of iron. And I've got a design for a ship which exposes a very large area of iron, which you want to have corroding, and it's corroding at a rate that you can set by the current that you are putting into the anode.
That's an interesting thought.
Correct. And the ship's driven by the wind, and they cruise around, and the iron is in the form of angle iron, which is very easy to replace. And you want, each ship can take several hundred tons of iron and come back 3 months later and load up again.
Stephen, could you do the same thing on an abandoned oil or gas well in the sea?
Yeah.
So that you could therefore watch the down current effect of that iron on the ecology.
Yes, wrecks do attract fish. That's well known to divers.
But this would actually not only allow the attachment to the structure of these encrusting organisms, but also would release the iron for the pelagic fish and the pelagic organisms.
Yeah, what you want is to have the mid-ocean iron concentration be closer to the concentration of iron in rivers. There's quite a lot coming into the sea from rivers. I don't think it matters where the iron comes from, but we just want a more small amount of it in a big area rather than an enormous great.
Even what you're saying is exactly the rationale for iron salt aerosol, that having a very low concentration of iron spread over a wide area, as distinct from the iron sulfate methods that were tested.
I'm sure that the Sahara stuff will be rather on the big side and will sink quickly. It may be that it's only the very smallest Sahara stuff that actually does a good job.
Very small amount getting captured.
Similar sort of low concentration you get from the buoyant flakes in the surface as they float round.
And if biomass builds up again and it all fertilizes itself and lots of phytoplankton comes back, that makes DMS for more clouds, better albedo. But the big the big problem is as soon as you've got lots of biomass swimming around in the sea, it becomes a huge magnet for fishing vessels. So this is
a little bit everywhere.
Beg pardon?
Do a little bit everywhere.
Do a little bit everywhere. Okay.
Exactly.
Yeah.
That is the whole point of some of the early experiments we're proposing to do with small island states who've got huge marine territories and big chunks of their economies based on fisheries. So once you fertilize an area around Tonga or one of these places, the licensing they get for their fisheries goes up. You share the income from that. The tuna come rushing in, who are thin to start with, and loads of food. They get fat, and you support the whole thing. But hopefully, as that happens, there is a net gain of biomass in the ocean, and it's become self-funding.
There's a problem, which is that as some kind of fish food gets rare, it also gets more valuable. And so there's a very strong tendency to exterminate the very last few.
Yeah, well, hopefully we overcome that and push it back in the other direction.
Oysters used to be regarded as the food of the poor.
Yeah. Actually, thinking of such things on food and switching out of the oceans a little bit today, Bolsonaro hopefully is out, and we have hopefully strong Amazon protection coming through. But then you start looking at the importance of how you pay those ranchers, cattle ranchers, for actually carrying out the forestry protection and regrowth that needs to be done.
Or at least protecting their existing soil, because at the moment they're mining the soil. Let them add biochar to it. Let them, do regenerative farming, all that sort of stuff.
Yes.
That's from your agenda.
It's okay. I did think that actually, but it's okay. Well, I actually sneaked something else in here as well. I don't know what people think about that, about ocean acidification, because this is often mentioned, and it's really a bit frustrating for Franz and I, because we worked so hard on a paper which we never really got time to finish. And I just wanted to mention that Franz,
that solves the problem. It takes the carbon out of the ocean.
Yeah.
Out of the ocean, and then that went away.
Yeah.
And turns the acid into oxygen.
Yep.
Yeah. Yes. Franz, I just want to mention that because I think I hadn't realized that you identified about 3 ways that, I mean, we all know that the phytoplankton, when they make organic carbon, they release oxygen. That raises the pH at the ocean surface. And when they make shells, we all know that they make calcium carbonate, that releases acidity. So they have a way to regulate their pH. You know, they can make more shell or make less shell. But you identified about 2 other ways that they can raise the pH, and then 2 other ways they can lower the pH. Is that right?
The main thing is the transformation of hydrogen carbonate to organic carbon. This produces pH increase, and when you can see and you measure it day by day, you see in the night the pH at the ocean surface is falling, and during night the pH is
during the day it goes up.
During the day it goes up again, and I think the acidification depends also on the stratification.
Mm.
When stratification restricts the nutrification of phytoplankton and and reduces production of organic carbon. So you get automatically an acidification.
Yeah.
People always, also oceanographers, believe the concentration of atmospheric CO2 would influence the ocean pH. That's wrong. Otherwise, in the Cretaceous times, you got huge amounts of coccoliths, which build up, for instance, the chalk around about Dover and so, and there is absolutely no sign of acidification from the sediments. If the ocean would be, they had up to 2,000 ppm CO2 in these times. Accordingly, the ocean had to be extremely acidic. That wasn't the case.
Yeah.
Otherwise, no coccolith would have grown in these times.
Yeah.
But back then, the life would have been adapted to those different conditions.
Yes, at least we have in the Cretaceous times huge amounts of sediments of carbonate.
The chalk.
Yeah.
Yeah. The whole Alps contain very thick layers of
dolomite
and other kinds of carbonate
from the Cretaceous.
Jurassic also.
Yeah. I mean, and you've kind of said that it looks as though the ocean has been round about more or less pH 8 since life began for most of the time.
Yeah.
With huge changes in CO2.
Even in the extremely huge amounts of CO2 in the Archean, you have carbonate sediments.
Right. Yeah. So it's there was some alkalinity. Well, there must have been enough alkalinity to make carbonate sediments. Is that what you're saying, Frank?
Or enough life to absorb the acid and turn it into oxygen.
Yeah.
Even before the oxygen time, you have carbonate sediments.
Right. For the great oxygen event.
Yeah. In the 4 billion years old sediments.
Yeah. And so when we came out with this, when Franz first started saying this about 2 or 3 years ago, I think you were there at the time, Robert. Franz said it's a fairy tale, that ocean pH is related to atmospheric CO2. It was we just, it was so controversial. Well, it's still controversial, but I think what we're really saying is the ocean, please consider that the ocean pH is regular, as James Lovelock said, to a large extent regulated by its life. Well, it can't be regulated by its life if there isn't any life there, because you've got rid of all the nutrients. Okay, so then it's just a body of water, and it is going to go up, according to simple physics, physics and physical chemistry. But if you've got lots of life in there that has numerous ways to raise the pH, you were saying before, Franz, when you just say that when they make DMS, that's acidic, isn't it? And so they can raise their pH by producing what it does that becomes DMS. But and there were other mechanisms you came up with as well. I just sort of keep thinking we should write those down and just put them up, at least so some other people can see those mechanisms. If the biology of the ocean can regulate its own pH, it looks as though they've been doing that for billions of years. Then it's no surprise that the ocean, that's how come the Earth has survived, that life has survived this long, because it regulates its environment, just as James Lovelock said.
It was a very different life. It started off 3.8 billion years ago and went through for 2 billion years. Totally different conditions, a different planet, different circulation. Sometimes it's been completely covered in water, sometimes it's covered in ice.
Yeah.
Sometimes it's very, and sea levels rising dramatically, and the amount of land available, and the position of the continents completely different. The circulation systems completely different. But within a timescale that, generally speaking, life can adapt to. Unless you get hit by an asteroid or a massive volcanic event, or humans, life is able to keep up with the change. But it's these massive events where it knocks it sideways, and it then has to stagger to recover and rebuild and change itself. It's in every case, it's always moving to stabilize and colonize and adapt its environment to be more suitable to it. And the other thing about natural things is that they are constantly evolving, becoming more complex and more sophisticated. So early life forms are considerably less sophisticated than the modern life forms. When I'm talking early, I'm talking 500 million years ago.
And there's some lectures from a guy called Nick Lane. I see him on YouTube. He's talking about how did life begin, and again, Franz talked about this. Because the issue was there wasn't any energy. If you've got no oxygen, I don't want to go on about this too long because I've snuck this in and it wasn't sort of agreed. But I find this very fascinating. So please shut me down if you think it's not relevant. There was no oxygen, and the main, before oxygen, the main oxidant in the ocean was sulfate. The ocean is still full of sulfate. There's lots of it there.
Yeah, but this sulfate came from an oxidation reaction.
Yes,
and
that's right.
This was the mechanism between catechol and the quinone.
That's it, quinones. Yes. So we could
and this could also produce sulfate, because in these times there was no oxygen there, which could produce a sulfate from H to S. But the quinones can.
So this is the general principle. To me is fascinating that it began. I said to Franz, well, how could life begin? Because he said that everything is a redox reaction. It's you need an oxidant and a reductant, and then they react, and then it makes energy. And so I said to Franz, well, how could life begin when there was simply no oxidant? There wasn't even any sulfate. And he said, well, there was a very strong reductant. It's hydrogen in the serpentine rock. And I said, but where was the oxidant? And he said, well, you don't really need a strong oxidant. Carbon dioxide, well, bicarbonate, or hydrogen carbonate, as it's supposed to be called, in the ocean is enough. This is sort of neutral enough actually be able to use as an oxidant with the hydrogen in the rocks, and there's microbes that still live on that,
But
and that was the first archaea life.
Clive, in these times, you had also photolysis at the ocean surface.
At the very beginning?
Yes, since about 4 billion years ago.
Yeah.
The big layers of how do you call it?
Banded
iron formations.
Yes.
Banded iron formation.
Yes.
They came from this early photolysis.
Yeah. Yes.
Because the ocean was full of iron too, and silica.
Yeah.
And at the ocean surface, microbes, the phytoplankton of this time were microbes which changed iron 2 with sunlight to iron 3.
Yeah. Yes.
And that's what made our giant iron deposits in northwest Australia.
Yes,
that reaction.
Yeah.
Yes, Australia, South Africa, or Namibia, or North America. The biggest iron ore concentrations are from these times.
Yeah. Yeah.
Probably the Ruhr too.
Oh, the Ruhr, right. And just as Brew was saying, things get more sophisticated. Then something came along that said, "Oh, I don't need iron. Don't need so much iron to do that. I'm going to do that with some other, chlorophyll or something, and I'm not just going to oxidize, have a slight change of oxidation state with iron. I'm going to actually make oxygen." Rubisco, and then everything had to change because entire
and these chemicals they used, these catechols, the microbes, the biofilms, used for dissolving silica, for instance.
Dissolving silica, yeah.
Silica and silicates and so on.
Yeah.
They are excellent chelators for iron and silicon.
Right. Yeah. So this is the whole thing, that it began with perfect chemistry for dissolving rocks, and the continents grew
because
very fast.
They needed the
nutrients,
elements, and these things are used until today.
Yeah.
The best iron chelators are, for instance, is this enterobactin.
Yeah.
Which extremely the most strong iron chelator known for iron 3.
Right. Yeah. So it's been a fascinating, but it's just between me and Franz so far.
No, that's really interesting. So iron, chelating iron 3 makes it soluble and retainable within cells. When you say most powerful, in what way? Is it just doing it at a higher rate per kilo, or what? How is that working exactly?
So I'm not go on. Sorry, Franz. Yeah.
They use it for different purposes. Dissolving a rock, for instance, to get
get the nutrients
out from there.
Is that the question, Brian?
Sort of, yeah. I mean, is this a bacterium? Is it a microbe? What's the organism?
They're all doing it. Loads of them are doing it.
These catechols are produced by lots of microbes.
They grow on your
What's
teeth.
the chemical they use to dissolve the silica?
Yes. They can.
Do you know what the chemical name is?
It's enterobactin is one to dissolve silica, but others things with there's lots of other chelators as well, aren't there, friends?
I can't tell you. I only know these effects of. I worked long in the groundwater contamination situation, and there you have always in a organic contaminant produces a reduced milieu, and then you have the groundwater, normal groundwater, which contains oxygen, and in these redox gradient zone, there are the microbes. They have lots of biofilms there because they have nutrients and oxygen there, and they live from these
from the gradient.
From the gradient, like we need also reduced things to eat, and we oxidize them by oxygen, and the same do microbes at these in this gradient zone, where they can take breathing from oxygen or sulfate or other oxidants, and take organics from the contaminant or also from natural contaminants.
And the principle applies everywhere. And so the center of
and there you find out in the oxygen zone, then you find the iron 3 precipitates, you find silica precipitates, and these precipitates come from the quinones. From they produce catechol for dissolving the rock, and the dissolved chelates, they come into the oxygen zone, then silica and so on falls precipitates, and there you find
you find the evidence of it.
Even they build up even a rock building.
These petrified rocks, petrified trees and things.
You find these, for instance, in the everywhere in Germany. We call them. The geologist's name is the cement quartzites.
What
the cement quartzites.
Petroliths or something?
Is in Australia you find them likely in the warm areas. Cement.
I know
these are sediments which are cemented by silica or by iron. I don't know.
Yeah, I can't remember. You've told me before, friends, and you get these wonderful diagrams, and people sell them as art because it's all these sort of not diagram, but pictures of all these sort of swirling sort of formation, and it's all rock. It's all kind of stone like that. Anyway, I didn't want to take too long. Yeah.
Everyone who goes on the coast of Dover finds these
flintstones,
concretions.
Yeah,
full of flint concretions. This is the same. You have a anaerobic sediment and an oxic seawater above.
And Franz,
then,
is that what makes the flint nodules in the Dover?
Yes, that's it.
Flint nodules, okay.
Yeah. This is a precipitation of quartz when these chelates oxidize to quinones. Quinones cannot chelate.
And that's what early humans used to make their tools with.
Yeah.
Yeah, permanently. Everywhere.
It's silicic ooze that then polymerized over presumably thousands or millions of years to become flintstone.
No, it goes rather fast.
Is it? A few hundred years?
It goes rather fast.
Yeah. John, you've got your hand up. John,
Oh,
listen.
Yeah. In chalk, you get nodules of iron, which are kind of amazingly kind of circular, and you get flints.
Yeah.
Yeah.
So those are two different kind of accretions that must have occurred over millions of years.
You know, the sediment contains these coccoliths, and they contain these silica algae. How do you call them?
Diatoms.
Yeah, diatoms.
Yeah.
Diatoms are made from silica. In the organic phase, in the reduced phase, the chelates are produced by the biofilms, and you dissolve silica from the sediment, and near the surface of the ocean, they are precipitating because the chelates oxidize. That's a simple process. For instance, in humic acids, there are also these
chelators.
Forms of chelating. You need a benzene ring with two adjacent OH groups. These are like catechols.
Yeah, we have to publish our paper, Franz, and they can read it if they want to.
Once we get ready.
One day. Yeah. Okay. Right. Okay. So this is another one of. Did you want to say any more about the? I mean, you explained it very well last week. I thought, Stephen. There's not much energy in for a huge energy reflected back out to space from marine cloud brightening.
Yes, the energy that you need to make a condensation nucleus is just its surface tension of the water and the surface area of the condensation nucleus, and you compare that with the energy that's reflected from the cloud drop that grows on that nucleus, and you get numbers that are a billion and more, and that's why we need zero material to make it, because the material is coming from the sea around us, and the energy is coming from the wind. So while you have this enormous energy gain. Now, you were talking about numbers of nuclei. If you're in a hurry, if you can double the number, you get a reflectivity increase of a bit over 5%. Okay, that works over quite a wide range. If you want to be a little bit more sophisticated, you can take the ratio of two number ratios of cloud drops, and if you take that ratio and you take the natural log of that, and then you divide by 12, that gives you the reflectivity change. So 1/12 of the natural log of the ratio of nuclei. And if you're in a rush, you can say that doubling it gives you a bit over 5% increase in reflectivity. So doubling the number of nuclei in a cloud gives you 10 times more than the problem. The problem is 0.5%, which is the excess that we're retaining, and doubling the number of condensation nuclei increases you by 10 times more than that, 5%. So you don't need clouds everywhere by any means at all.
Yeah.
And
amazing, yeah. And I read the Ahern paper. Is it Ahern? But it seemed very high quality. Lars Ahern, saying that you don't even need clouds. You can just make droplets and as sort of a haze, and it has about the same effect as brightening clouds.
Well, the complication there is that if you haven't got any clouds, you've got a much longer life of the aerosol. The aerosols are washed out by rain. So clouds, there's no rain, and therefore just hangs around until you get somewhere where there's the right relative humidity increase.
Yeah.
So that's why it's just as good to do it when there's clear skies.
Yeah.
It's probably better to do it under clear skies because you get a lower dose over a bigger area. You don't want a high concentration in a small area because it's that log term. Remember, I said it's the log of the 12th of the log of the number change. So
Right.
because it's a log thing, you're better to have double the area and half the dose. So you can do it anywhere where there's clean air, and you get clean air after it's rained. So the best place is to look for where it's just rained and then go there and then just wait.
And put it up there and let it last a long time. Yeah. I'm thinking that might be best for our aerosols that we're talking about that take methane out of the air.
Yeah.
Because you'll get more bang for buck. You know, they'll last longer. They'll keep depleting methane instead of getting rained out a few days later.
There is one other effect, which is that if you have a number of vessels that are cruising parallel to one another, they will make lines of cooler air and cooler water underneath it. And this would be just exactly what you want to get a rotation from cold water sinking and warm water replacing it. So you can actually increase the mixing, you can reduce stratification, and that's probably a good thing too. I haven't done any sums on it, but it's bound to be in the right direction.
You get the same effect if you have mycetomizers in a row with gaps between them. The wind downwind, you'd have some areas with cloud forming and clear areas between.
Yeah, and that's a good thing to do.
And then there's is there any other points on that? I found I'll just say once again, your paper is very useful, Stephen. I want to reproduce those calculations from Julius Lingo, and just take that what you've just said there with the 12th log. That's part of that, I believe, isn't it? The 12th log.
Well, I can send you. I'll send you a paper by Schwartz and Slingo. It's not the same Slingo; it's her husband, which explains the Toomey effect. Toomey did lots and lots of flying of airplanes and diving into clouds and scooping out drops and measuring reflectivities and drop sizes and all that. He wrote for other cloud physicists rather than for Joe Public, and it's heavy going. But Schwartz and Slingo did a very good analysis of all his papers and for produced stuff that other humble mortals couldn't understand. And Schwartz and Slingo are probably the best way to learn this.
Okay.
It is Andrew Slingo. He died rather young, and Julia Slingo was his wife, and she was then the chief scientist at the Hadley Centre. She did quite a lot on the Indian Ocean monsoons and the temperature gradient on the Indian Ocean, but she's very hostile to geoengineering. I went to had a long debate after she said that it was useless and there'd be not necessary. There'd be lots of negative feedbacks that would save the temperature problem, and she had a go at Peter Wadham's, and I wrote to her with copies to the Common Select Committee, and in the end, she said we must have a discussion about this. And Peter Wadham's and I and Alan Gadian went down to Exeter to the Hadley Centre when we wanted to have a discussion about marine cloud writing, and she just wanted to give us a talk about how wonderful the Hadley Centre was. And we were just too polite to interrupt a lady. This is the problem about the way men behaved in those days. You couldn't say, stop that, listen to me. We just had to listen. And then suddenly at the end, she said, well, what a pity we haven't got any time left. And so we spent hundreds of pounds flying and putting up the hotels and things to no effect at all.
She's she has been shown to be absolutely wrong
2 minutes,
on the
I'll be
Arctic
right back.
ice.
Yeah.
Yeah.
And she's now living really quite close to Alan Guardian, and I think she's mellowed a bit. And she,
Here's what I found.
that's my telephone, which is talking to me. I didn't realize this. It's picking up things that I'm saying, and if it's got something interesting, it'll chip in. But she may be, now she's retired, she may be not taking messages from the government.
Too late.
Clive has just vanished.
Stephen, you were going to explain about insulation.
Right, well, the picture that I sent him was something I got from NOAA, and it's just showing a map of latitude vertically and months of the year horizontally.
Yes.
If Clive comes back, he can show it. If not, I can probably find one.
Yes.
And it shows that there's more solar energy going into the South Pole for a short time than there is going into the equator. It's 550 watts per square meter into the South Pole, and it's about 440 going into the equator. And can you bring that up, Clive?
Yeah.
Yes. So you got this 550 down here for the Christmas period, and then there's absolutely nothing at all in the winter. And if can you scroll down to the other side, you get the North Pole, can you?
Yeah.
You've got the same effect here. It isn't quite as extreme because I think of the tilt of the atmosphere. So the mean run here about the equator is about 425 or so, somewhere
Wait a
between.
minute, why isn't it symmetric?
And you've got 550 at the bottom.
Why isn't it symmetric in the northern and southern hemisphere? This is confusing. At
Yeah.
30 degrees south, you've got 500, but at 30 degrees north, you don't.
That's right. Well, you've got, I need to look at that's 400.
Yeah.
That's
Look at
Well,
the-
you wouldn't expect the symmetry, Brian, because of the Milankovitch cycles.
Okay, you're talking about the 5%
Excuse me, folks,
eccentricity.
I've got to leave you. I have some extreme wind here and I've got to go and secure some things outside fairly quickly.
Good luck.
Okay.
Bruce.
Bye-bye, Bruce. See you in a
Bye.
couple of weeks.
Okay,
Yeah.
so we may be, all right, so we're closest to the sun in January. And which month of the year is the horizontal axis?
Yeah.
Where would January appear?
So this is January in the in the Arctic. Oh, that's right. So that's January in the Arctic. So that must be midsummer in the
closest to the
Arctic.
sun.
Yeah.
Okay, now it makes
The
sense
southern
because
hemisphere
we're
is brighter than
closer
the
to
northern
the sun.
hemisphere.
Okay, I'm with you now.
Yeah.
Thank you.
These numbers are just for these colors.
Hmm.
And so the numbers are not the same going along this way.
Well,
But-
the colors are different also, and that is explained by our greater distance to the sun in the northern hemisphere summer.
Yeah.
The x-axis is wrong. The x-axis should be date, but it's got
It should be
degrees.
months, yes.
I think it's the days of the year, effectively.
Yeah.
But we can
Sort
we
of
can error
angle.
correct.
Yeah.
So yeah, 90 is the June solstice, and 270 is the December solstice.
Well, now I understand why we get bad sunburns here in Australia in the summertime. We're just closer to the sun.
No, we're 10 degrees closer to the equator than the United States.
Ah.
Well, there's some of that, but for a given latitude, I mean, I've lived at 28 degrees before, and still there's more UV, and I think it's explained by the distance to the sun during the summer.
So that's what it is. It's the elliptical orbit.
Yes.
Okay.
We're
There we
at
go.
perihelion in January right now.
Right. A perihelium, did you say?
Perihelion, yeah. And that
Perihelion.
next color of orange is 450. So it looks like there's 10% less sunlight hitting the northern hemisphere at 30 degrees north.
Here.
Yeah, look at that, because that's that same color 450, right?
Where are we? So we're talking about the winter here, are you?
Yeah, the 450 contour
Yeah,
is
this
equal
one.
to the 500 contour. So basically the
Yes.
450, you're getting 450 at 30 degrees north, and you're getting 500 at 30 degrees south. So there's a 10% difference in insolation.
Hmm.
Fascinating.
Yeah, we get 4. That's
10% difference in UV as well.
Right.
Imagine.
Okay. Yeah.
So
Yeah.
It's a fascinating chart. Thank you for that.
Yeah. Yeah, sure.
Brian, you did your doctorate on Milankovitch cycles, so you must understand all of this stuff pretty well.
Yeah, ironically, I mean, I hadn't seen it. That chart I hadn't seen. It was my undergraduate thesis at Princeton in physics, and built an early 2-hemisphere model for Milankovitch forcing, and identified that approximately 70% of the historic ice age record could be explained by Milankovitch cycles. The remaining, so that's a lot of the variance. Of course, we just canceled the next ice age, and now we've the anthropogenic effects have greatly swamped anything that Milankovitch could have dreamed of.
Mm. Yeah. Okay. And Franz, also, it seems that because the Milankovitch cycles, they used to be that the change in temperature of the Earth going back several, I don't know, is it 10 million years, for a long time, the temperature varied with the Milankovitch cycles, but I think starting about 3 million years ago, it wasn't every time, so it seemed to get stuck in a huge glacial period. In fact, they were getting worse until we came along. That they were like about 4 Milankovitch cycles, it would get stuck, and it would take. And so this is what Franz found a paper that said, and then what gets it unstuck when it's deeply freezing cold is the air is so dry that you only need a few forest fires or a bit of dust. I think it's dust, actually. The dust blows onto the ice sheets, and then suddenly it warms up and it goes in the other direction. So you get history.
That's the Ralph Ellis paper from
Ellis.
2016.
Ellis, yeah. Ellis and Palmer.
Ellis has a very notorious reputation. But that paper, I think, is the only thing of his, because it's co-authored, that's reliable. And what he proves is that the turnaround in the Milankovitch cycles is primarily a function of albedo rather than carbon. So putting albedo into its correct place as a climate forcing driver, as the principal lever, is a really significant outcome of that paper. Because the thing is, if you've got rising carbon, then you expect it to just continually get warmer. But what happened in the sawtooth of the glacial cycles was that when it got very warm, suddenly for some unexplained reason it turned around. So the turnaround of the sawtooth every 100,000 year pattern of the ice ages is not explained by the conventional reliance on carbon dioxide, but is reliant on dust, on albedo as the primary driver. And that's why we need to shift our climate focus from carbon to albedo.
That's very significant. And is it dust in the atmosphere or dust on the ice that's making black ice?
I think dust on the ice at last.
Okay.
What happened was that when the CO2 level got down to around 180, it was too little amount of carbon in the air for trees to live. So the tree line collapsed, and that then generated massive dust, which covered the ice with black, and that then generated the turnaround every 100,000 years. Is Ellis's theory? To me, it's quite plausible.
Yeah. And furthermore, it would explain the asymmetry that the melt cycle is very fast, and then the refreezing occurs much more slowly.
Which is another mystery in the conventional approach.
Well, given the two separate and disparate phenomena, one being dust albedo and the second being a gradual cooling and refreezing, it makes perfect sense that they have different timescales. But it's also ominous from the present situation, because it means that the timescale for warming and melting in the Earth system is much shorter than the timescale for refreezing. under natural
Yes.
conditions. So it means a lot more work to do to go back the other way.
And the only lever we have is albedo. Carbon is not a lever.
I think it's a very good point you make, Robert. I hadn't really thought of using that and saying, because people say, oh, no, you can't do this because it's so unnatural, you know, you're playing with the system. We say, look, this is what happens. This is what caused the very abrupt ends to the ice ages. And so don't think of this as some alien thing that we're trying to do. This is a very important phenomenon or important component of warm, you know, what maintains the temperature or changes the temperature. And if you ignore, we ignore it at our peril, because look, this is what's ended the ice ages. So I think good to link it in like that, as you've done. Yeah.
Thank you, folks. This is all just for my presentation to AGU this year. We need to understand the operation of the Earth system in order to deal with the climate crisis. I
think Ellis's paper is mainly due to his co-author. Ellis is actually quite a kook. He's notorious as a climate denier, and so you know, there's lots of climate deniers who sort of link into this solar radiation and Milankovitch stuff in order to challenge climate science. So be careful. But his paper that Franz mentioned is an excellent paper.
Yeah.
So what's the Ellis paper called?
Ellis and Palmer.
Ellis and Palmer. Yeah.
I'll post a link.
Great.
Yeah. Okay, we've got 10 minutes, folks. And so, well, how about talking about, I don't know, what do we want to talk about next?
Go for atmospheric river.
Yeah, I think that makes sense. Yeah.
Well, yeah, this was just picking up on a discussion, one of Meta Spencer's town hall talks with Paul Beckwith and Peter Wadhams recently I picked up on. And Paul was explaining the atmospheric river that's the deluge, massive deluges, southern Eastern Australia is suffering. And it's like 16 times the volume of Sydney Harbour. You know, it's a water vapor above the clouds, which is travelling across and dumping. And of course, it's the Antarctic jet stream, and how it's disturbed. Of course, it's raining a lot more on the ice in both the Arctic and the Antarctic, and that's accelerating melting, which is disastrous as well. But it's just the scale of this. It's just amazing. I mean, kilometres wide. It's this river in the sky, which is coming up, and it's very disturbed. So, and this seems to be happening in the Arctic and the Antarctic in the sort of at the same time in the shoulder season. So, yeah, it's very disturbing. And of course, they talked a lot about sea level rises as well. But just an interesting discussion. I think you'd all be across this as well, no doubt. But I think we need to study the Antarctic jet stream a little bit more than just the Arctic jet stream. The two are misbehaving at the moment.
But what I wonder is what scope there is for marine cloud brightening, or you know, putting particles in the air, nucleated particles, for reducing these massive floods and making it rain where people have got droughts. Can you answer that, Stephen?
There's a tug of war in two directions. If you put higher temperatures, the sea evaporates more, and that water's got to go up, and it has got to come down somewhere. And that's one thing. The second thing is that to make rain, you need to get big drops falling down and gobbling up smaller ones to make an even bigger drop. So if we make more but smaller drops, you've got a sort of balance and fight going on between the two things. And it may be that you get a stronger monsoon if the sea is cold and the land is hot. All right, but you're getting less rain over the sea. because it's not able to get the drops big enough. So you might be getting more water transferred to the land, and that's probably a good idea if it's not done too much. But if it is done too much, then you get a terrible flood. What we'd like to do is have a little bit for more for longer periods. And I think if we knew exactly where and when to do it, we could make more precipitation over the deserts, and we might find that we can make the monsoons be longer but less severe. All right.
With marine cloud brightening, we've got the chance of moderating and extending the rainy season. So you don't get the floods, but you do get irrigated pastures. And we've even got a chance of, by choosing the size of our particles, to stop it raining when the harvest's about to come in, and therefore making the harvest better.
I raised this argument in my interview with Robin Williams on the ABC Science Show on Saturday, which I've just put the link in, and that gets a very wide audience. And it was actually a previous meeting where Hubert Hubbard put me in contact with Robin that led to that interview, and they get a very wide audience. And that program's been running for nearly 50 years with Robin as the host on the urgency of geoengineering. But what I said about marine cloud brightening was that it's a wonderful technology that can be used to manage the weather. And because, as Stephen has explained, the targeted cooling of the ocean surface can regulate the El Nino and La Nina cycle in the Pacific, and also the Indian Ocean dipole. And generally, the cause of atmospheric rivers is the high sea surface temperature. And so by generalized cooling of the sea surface, the excess humidity in the ocean that has caused the atmospheric river that's destroyed Lismore, and that's likely to destroy California in the future when their cycle turns, can be regulated and modulated.
There's a paper by some people in the Cicero labs from Norway, Stern, and all they did was a bit more intelligent than most of the climate modeling. They just increased the condensation nuclei concentration by 50%, only where there was already a low cloud. And this did increase precipitation in all the desert bits, the Sahara and Australia and Mexico and places and South Africa, by about 10%. Now, 10% of bugger all isn't very much, but it was increasing. All the really big reductions in precipitation were all over the sea. And there'll be people living in small islands who would object to that, but we could very easily provide desalination to people who live on small islands to make up for the missing rainfall. I will send a map showing all this. It looks a very, very benign thing to do. It also showed a lot more cooling in the high latitudes over Siberia and Greenland. There was a little bit of cooling in quite a lot of places, but most of it was in the north. Now, why it wasn't doing so much in the south, I don't know, but maybe that's because the clouds would just doing it, spraying where there's low clouds isn't a very complicated rule. I'm sure they could find a better way than that, but it was so much better than what all the other models have done, which is just to treat between 30 north and 30 south, rain or shine all year round. So that's Stern. I'll send, if I send it to Clive, will you circulate it? I think I've sent it.
Why not just put it onto the NOAC meetings? Just reply to that email address. It'll go to everybody, Stephen.
Okay, right.
And then you don't have to wait for me to do it.
Right. Okay.
And I will look at it anyway. Certainly when I get time. and I'll get to it. Thank you. Much appreciated. Right, what else? Any more about
the Healthy Planet people are going to COP27, Peter Fiskalski and that, and I'm hoping that the Indians from the National Institute of Oceanography will finally have their buoyant flakes paper out on the slow release of iron in the surface waters from them. They had a bit of difficulty with their experiments earlier on, and they've been trying desperately over the last couple of months to do experiments to show that.
Okay, great. So you're hoping for their paper to come out in time, you're saying, or in the next few weeks?
Or they'll probably do it as a side event. I'm not quite sure where they're going to publish, but hopefully that side event will get some interest, and the HPAC's people will show the importance of albedo.
Right.
The Indians have very good climate modelers and climate generally, because it's so important to them. My grandfather was the second director of their climate modeling thing, and he trained up the third one, who is an Indian, and he was trying to understand monsoons back in the 1920s. And, I'm walking proof that the ability in meteorology is not genetically related.
Or is, if that was your grandfather.
My dad did inherit it. He was a meteorologist in the Navy in World War II, and he had to find places for aircraft carriers to go where there was a 15-knot headwind. And if he got it wrong, the planes would crash over. You couldn't land properly. Very heavy American fighters on rather small aircraft carriers. So that was a challenge to get your wind predictions right.
You think he didn't have to work for Putin, get poisoned for failing or something?
No. Yeah. The war came to an end before the aircraft carrier. They turned around halfway to Japan, but they were going to be invading Japan, and the atom bomb dropped, and he
turned around. Good idea.
Well, could I just ask a final question to Brian, whether the Australian Academy of Science got back to you?
I haven't seen it yet, but when would that have come through? Because I'll search for that email now.
No, where you were going to, you asked if you could speak at their conference, and did they let you?
I'm not sure. No, I don't think I got anything back from that. No, it was quite a cold edifice. I'm not sure we got any response.
That's because you're treading on holy ground. You mustn't do that.
Well,
I congratulate
holy sites.
Australian Academy of Science. I think congratulations, first of all, Robert, on your interview this weekend with Robin Williams. I'm looking forward to listening to it in detail. And if there's a follow-up, just let me know. I'll be happy to engage.
Right.
When is it being broadcast?
It's already broadcast. I think
it was broadcast on Saturday. I put the
okay. I must listen.
Yeah, please do.
Yeah, that's fine. I think the Australian Academy of Science, exactly. The Australian Academy just put me on their mailing list. That's it. That's all we got for our trouble.
Oh, well.
Some you win, some you lose.
Exactly.
Did we want to hear about the SAI conference in Colorado? I mean, we're up to our 90-minute mark at the moment.
Yeah, I think it would be lovely.
Is there a link to that conference?
I will send the links to it. You can play back any selection from it. There's a sort of time scrolling on the bottom, and you can skip what you don't want. But it's really all about stratospheric sulfur.
Any good bits which you picked up, Stephen?
Not really. I was listening out for what I thought would be interesting to me and rejecting quite a lot of the other stuff. The scrolling through is really, really quite good. It's a very efficiently run conference, and it's done at NCAR in Boulder, Colorado. which is where John Nathan used to work.
Right. So actually, that's wonderful. And to that end, I was just discussing Arctic stratospheric aerosol injection with Cambridge last night. And I'm curious if you find anything that would be a technical barrier to the notion of having just the existing airliners switch to a high sulfur tank north of 60 degrees north to achieve at orders of magnitude lower cost an injection at, the tropopause is 12 kilometers high up there. So it's so easy to actually achieve that with a limited time scale of months instead of years.
You'd have to be sure that what the sulfur did to the jet engines.
Right. I thought there was high sulfur fuels have been used for decades, if not centuries. So I'm curious, is there some way that we can go back to the old sulfuric fossil fuels and have it work all right?
Wasn't that mainly on ships, not on planes?
I think it would work on planes as well.
Right.
But,
and the question was, didn't we used to have high sulfur jet fuel?
Well, what we had was sulfur that was infecting babies' lead. And so the regulation is about not allowing to have sulfur in motor fuel. And so the old companies had to take sulfur out of the motor fuel and had to get rid of it. So what they did was put it in ship bunker fuel. So there was particularly high sulfur content in what the ships were burning. And I remember reading somewhere that there was more horrible stuff in Los Angeles from the ships than from the cars. And that, I think, perhaps is believable. It shows you how much sulfur there was in ships. And now they've been prevented from doing it. And so we're going to get quite a lot of extra warming because we're not putting sulfur into the stratosphere anymore.
We're not putting it into the troposphere.
Motor fuel. Right.
Well,
yeah, there's tropospheric aerosol in there.
Stratosphere.
Yeah. I mean, ship tracks are just making clouds from sulfur dioxide. Just
yeah. You can see where the ships go by looking at the sulfur dioxide.
Yeah.
In the
ship tracks. Yeah.
Agreed. So this question, the babies were getting affected by the sulfur in motor fuel?
They were, well, they had to put lead in the motor fuel to stop knocking, and that was they were not allowed to put in lead anymore, and they were finding that babies living near roads were getting lead up to dangerous levels, which is stopping their brain development apparently.
Yes, no, that's very well documented. I guess, how is that related to sulfur though?
Well, the general thing about cleaning motor fuel, not just from lead, but for other stuff too.
I see. It was just a general trend.
Yeah.
And the question is, has jet fuel ever had higher sulfur levels?
Pass.
Okay. And I'm wondering, maybe Franz has some thoughts on this. Is there some sulfur chemistry that could be less corrosive on a jet engine? Right. Oh, that'd be great. John's got friends.
No.
Yes.
Really, you can put it in the fuel. There is no problem with the corrosion. I think SO2 is not so corrosive when it oxidizes.
You could probably just have elemental sulfur put in as the jet exits, so it doesn't go into the engine. You just inject it into the
afterburner,
the
exhaust. Yeah.
I'll tell you, just from as a pilot, it's so much easier to just have it be a mixture, in the fuel. And that tank is only selected higher than 60 degrees latitude, and it's so easy for the pilots to just switch tanks and you're on your high sulfur fuel and then turn it off again.
Yeah.
Right.
Yeah.
And then we can see if John is right about.
I know it's quite a strict specification for aviation fuels. The new airport in Adelaide was held up for months, and then this friend Colin was called in. There was some slight contaminants in the tanks, and they couldn't open the new airport. So it is quite a strict spec, but whether it includes sulfur or not, I'm not sure.
Yeah, well, when you weigh on the balance, business as usual and a melted Arctic, I think we'll find a way to make this work.
Yeah, I think the worry is that anything in the stratosphere, any particles in the stratosphere, are a catalyst for release of chlorine that attacks the ozone, and so there's been this controversy, and then they've said, okay, well, we won't use sulfur dioxide, we'll use calcium carbonate. But Franz has said that well, anything, it doesn't matter, any substrate is unfortunately a catalyst for release of chlorine. But
agreed. But now the benefit here is if we are selective with latitude, and if the modeling is correct, then a seasonal injection in the springtime will result in 6 months, summer and autumn, improved reflectance.
Yeah.
And by the time you care about ozone, which is in the winter time, you depleted the Arctic or the polar levels of sulfate due to the normal stratospheric convection and the descent into the troposphere near the poles. The model, the notion is that you want to time this so that you've pretty much lost your particles by the time the winter comes along, and that's when the ozone chemistry is so important.
I've had lots of arguments with John Lissons about this, and I think that what goes around comes around, and what falls may go around back to the equator and back up again and go round and round. And some of it may come out, but small stuff and gases mix, everything gets everywhere.
Okay, so the real question is this: if the stratosphere is moving into the troposphere, I know for a fact that the rainfall that we're getting in the troposphere does wash out the sulfur very quickly. And so then it's really, are you talking about some fraction that isn't getting rain in the troposphere? Well, we're getting rain storms all the way up to the tropopause, I suppose. So let me know if there's some flaw in that reasoning.
There's much less rain high up.
Sure.
So
well, lots of snow.
It's a question of how far down in the troposphere you get your rain. But it's things are much drier in the stratosphere.
Agreed.
But,
all right, we'll have to understand the upper troposphere then to characterize that more fully, but I wouldn't be surprised if it has to actually traverse many degrees of latitude, if not getting, I mean, I was under the impression that you've got 3 Hadley cells, but you only have 1 stratospheric cell from equator to pole. And thus it may have to get all the way, you may have to traverse almost to the equator for reinjection into the stratosphere.
Well, we need to answer that question.
I agree.
I'm not sure that it's relevant, because if the SO2 falls out from the stratosphere into the troposphere, you'll still be doing some cooling, but it won't be for very long because it gets washed out. So if there was some circulation back through the troposphere, it wouldn't matter.
Right. Yeah. So it's time scale, and of course, there's little ozone in the troposphere itself. So it's really just the amount that could actually get into the troposphere, avoid the rainfall, get back in the stratosphere, enough to affect ozone. That's an interesting question that we could analyze with modeling, and perhaps some people at NCAR at the SAI conference could actually, have some thoughts on this. So be interested in any highlights that might be relevant to this question.
But I think if any trial would be made, they should also look what the UV depletion is by such stratospheric aerosols.
Agreed.
And I believe that's not so good.
That's what I should have said. I meant to say that. The loss of UV affects the oxidative power of the troposphere. So essentially the methane sink, where UV makes OH radicals and makes Cl radicals, a little bit of Cl radicals as well.
We've had this conversation before.
Yeah.
And
but we haven't.
And concerning the UV there might be kind of 2% reduction in
Yeah.
UV, which would actually help to lower skin cancer by, I've heard
4%.
it's about double. So 2% reduction in UV would,
I think 2% is not much, so it doesn't.
Would be 4%.
Yeah.
Yeah. It'll be appreciated in Australia, where we apparently have 10% more UV and 20% more skin cancer.
Right.
So, so we should do the inject in the southern hemisphere as well as the northern, which is what is being proposed as a matter of kind of keeping the planetary balance. You don't want to be accused of upsetting the balance.
You're going to make it worse,
We've abandoned balance years ago, and now we're just trying to avoid Armageddon.
Yeah.
By the way, I would recommend Greta's book, the Climate Book, which is going to be released in the Northern Hemisphere in November 1st. And I did have a chance to read it this weekend, early release here in Australia. And the audiobook was wonderful with 3 or 4 excellent readers. And it's quite a tome, if you will, on the summary science on very broad terms, but also a political call as well.
But it's a call for CO2 emissions reduction, isn't it? Almost entirely.
It's sadly a bit Luddite when it comes to geoengineering proposals, but I'll have to read it again to get into the detail.
One of the authors, Naomi Klein, is vehemently against interference with the climate system.
Not that we have interfered already.
I know. It's a false argument. But
look, there's no pristine ocean anymore. Let's get over it.
Yeah.
We've never done it deliberately before. We've done it hugely inadvertently, like we've actually cooled the planet pretty successfully with SO2. So,
well, I think it's deliberate now. I mean, just driving your car around or flying, we know what the effects are going to be. It's probably distributed. Ignorance of the law is not an excuse anymore.
Well, folks, that's our time. Any last comments or questions, or even
yes, Kyle Kimball is giving some kind of talk on the 6th of November.
About what?
Well, he's the fellow. He's got an email address because he works in Estonia, but he's actually from California.
Can you remind me? Yeah.
Yes, he says his title is something like "Faster Than Usual." IPCC aggravates global warming faster than usual.
Oh yeah.
So he's blaming IPCC for the climate crisis, and the fossil fuel companies are pulling the purse strings of IPCC. So everything that comes out of IPCC is vetted by these by people who are under the fossil fuel companies' control, and hence you get understatements of the seriousness of everything.
Okay, so that's what his talk's going to be about then, is it? On the 7th of November.
So he's not into climate intervention, but he's into the ghastliness of this setup.
Okay.
And it's terrible that the climate activists think that the IPCC is the font of all wisdom, when in fact it's the font of disinformation.
Okay, so I guess you haven't had a chance to put a link in the chat, but you'll send an email.
I'll
we
have
can look
to
out for an email.
I've got it on a different machine, unfortunately.
Yeah.
I can't.
Yeah. Okay, Brian, you're raising your hand. Oh, you're raising a thumbs up. A thumbs up.
Yeah. No, I think it was a thumbs up, but basically, I would even claim that the term climate change may have come from the fossil fuel industry, and we should start using climate disruption as a much more accurate term.
Yeah, climate disruption. That's a good thought.
Yeah.
Let's
Okay.
head back to peak life. If there's some time of peak life, let's head back to that.
Get back. Yeah. From disruption to peak life. Yeah.
That's right.
All right. Thanks, everyone. That's well past our bedtime. Well past our hour and a half. See you in a couple of
Thumbs
weeks.
up
Thank you very much, everybody.
Bye, everyone.
See you soon.
Bye.